The least squares equation gives us a simple model to use to make predictions about data where there's a linear relationship. Now, being able to compute things is great, but you really need to know how good of a fit that model is and how accurate your predictions are going to be. Because if your model doesn't really make sense, then there's no point calculating anything. Now, the first sanity check is always take your data, make a scatter plot. Can you see if it looks linear? Now, that's a good common sense, but it doesn't tell you everything you know. Sometimes you can fool yourself into thinking that there's a linear pattern, even when it really isn't appropriate. You can always put a line through any data, but that doesn't mean you should be putting a line through every data. Now, how good of a fit is that least squares line going to be to the data? Now, what we really need to do to answer this is to study the kinds of variation that we get in our data. And when I say that, if we're talking about a line, let's say there's our regression line, if we start from one point and go to another point, some of the variation in the height here, I'm going to call this the total variation. Some of that variation is due to the linear model, right? We're expecting the y values to change because they are linearly related. And then some of it doesn't come from that. And then this is scatter. Or you could think of it as error from the model. So the total variation is made up of some linear portion and some error portion or some scatter portion. Now we're hoping that the scatter portion is very, very small and the linear portion is the majority of it because we want it to be a linear model, a good fit. Now to try to make it a little bit more technical, you could figure out here that, hey, the point x bar, y bar is always a point on your linear regression line. So you might have to go look at the notes a little bit earlier, but the parameter beta naught with the hat was given in terms of x bars and y bars. So if you go ahead and you replace it in here, you'll get your prediction, your line of prediction could be given by this formula. So that means your line of prediction could always be given by some sort of formula that looks like this. Now, I'm hoping that you can see if you pick x to be x bar, then you will always get y hat equals y bar. And that tells you that x bar, y bar is on the line. So regardless of what line we pick, it doesn't really matter. So we're going to use that to try to quantify this a little bit more. And we're going to quantify in terms of data points. So again, just for reference, let's say, here's my line. Now I know that the point x bar, y bar has to be on that line. It's always there. And let's talk about some other point over here. It's going to move over some distance, and there will be a total variation from that center point relative to this point. So I'm going to give this two different names. I'm going to say xi, yi for the observed, and up here, or sorry, for yi hat, and that one is the one we would expect from the prediction. But up here, xi, yi is the one we actually observed. This total, so even before that, you could think of it like this. You could think of yi, the observed, minus y mean. So that total distance, you could think of it as a sum. It would be the sum of yi minus yi hat. And this would be, you could think of it as the error plus yi hat minus y bar. You could think of that as the linear part. For a lot of different reasons that we're not going to get into, we're going to talk about the sums of each squared term here. So we're going to say that SST is the sum of the square of the total variation, and that you could think of as sum of yi minus y bar, all squared. SSR is the term they use. It's the sum of the square of the regression, or the linear portion, and that would be the sum of all of these yi minus yi hat. Oh, sorry. That's the one. Oh, sorry, I keep making a mistake here. And SSE is the sum of the square of the error, or the scatter. And this would be the sum of all of these yi minus yi hat, all squared. We're going to make a definition. So in terms of these three things, we've got a total error, a predicted or a linear error, and an observed or scatter error. So we are going to define something called the coefficient of determination. And we're going to give it the symbol capital R squared. And the definition of this coefficient of determination is going to be the sum of that regression error over the sum of the total error. By this definition, this thing can only be in between 0 and 1. And note, if there is no scatter, then all of these yi minus yi hats are 0, and their sums are all 0, and that means SSR is equal to SST. It's a perfect line, and that means R squared would be equal to 1. So a better fit means that this R squared is closer to 1. A worse fit means that the R squared is closer to 0. Now, just some notation. The capital R squared is the definition. We use little r squared for observed value that comes from the data. Now, your calculator, or R, is going to be able to calculate this. And in fact, that's the only way that we're going to go about doing this. You can show that in the farms example, that this R squared is 0.977. And that means that 97.7% of the variation in the Y values, or the output values, is due to a linear relationship, and about 2.3% is due to error or scatter. Now that means this is really good. Between the picture that we got, that looks pretty linear, and between this calculation of R squared, which is fairly high and fairly close to 1, we can be pretty confident that this is going to be a very good model. So we'll show how to use technology to get these values, and it makes life simple, but these are the basic concepts. We can postulate a linear equation, we can build an equation from data, and then we can do a very simple check with this calculation of coefficient of determination to assure ourselves that, yes, the model will be accurate.